Cordial greetings to the attendees of this webinar, greetings to the presenters, and thanks to the IFCC for giving us this opportunity to express the work of these three professionals who are members of the Interdisciplinary Committee of Experts on Quality Specifications and who will talk to us today about the importance of using the state-of-the-art tool as a minimum consensus specification. Since what matters is what they will express, I won't take up any more time and we will start with their presentations. First, the first speaker is Dr. Jorge Morancho Zaragoza, who holds a degree in chemistry from the Central University of Barcelona. He is a university expert in statistical methods in health sciences from the University of Barcelona and has been a professor since 2015 in the master's program in biological analysis and laboratory diagnosis at the University of Granada, and he is the technical director of the Spanish Association of Clinical Laboratory and the Spanish Association of Medical Biopathology Laboratory Medicine since 2005 to the present. He has been the technical director of the continuing education program of the Spanish Association of Clinical Laboratory since 2017, and he is a member of the Interdisciplinary Committee of Experts on Quality Specifications since 2009 to the present. Dr. Jorge Morancho Zaragoza, I leave you your space, and we listen to you. Hello, in this talk I will discuss the calculation or obtaining of quality specifications for the analytical phase based on the state-of-the-art. The information presented will be collectively obtained by the Interdisciplinary Committee of Experts on Quality Specifications. I will cover 8 elements in the conference. First, I will talk about the objectives, then the context where quality specifications based on the state-of-the-art are recognized, which is the 2014 Milan Agreement. I will define what state-of-the-art is, present how values can be extracted from the state-of-the-art in different ways, and we will compare the values obtained by these different ways of knowing the state-of-the-art, and then we will confront an example of the state-of-the-art versus desirable biological variation to reach some conclusions, and then I will talk about the bibliography. What happens? Flexibility is talked about because when there are specifications for each of the levels, the strictest one should be chosen. The way to calculate these specifications based on each of the models is in different situations. For biological evaluation, a great effort by the European EFLM has been standardized to propose how different authors could establish specific values. In this case, for the calculation of biological evaluation components to derive specification values. Model 1 and 3 are not standardized. Model 2, there is a database that can be obtained through the internet, which is EUBIVAS, where a limited but important number of measurements appear. For Model 1, on the other hand, very few results can be obtained in the scientific literature. For the state-of-the-art, there is a limited number of measurements, and the main limitation is that they can only be covered by those measurements controlled within the historical quality evaluation programs. For example, in our case, we have worked with 143 measurements. Finally, it is worth mentioning that there are no quality specifications for all and each of the methods, nor for all measurements. There will always be measurements for which it will not be possible to obtain any type of specification. Defined as we engage in the Milan Consensus, we can make a linguistic approximation to what state-of-the-art means. For Cambridge people, it would be the state of an activity as modern as possible and in the best situation. Interestingly, Cambridge translates the concept of state-of-the-art into Spanish as the latest model, the cutting edge, while the Royal Spanish Academy and the academies of the Spanish-speaking countries present state-of-the-art also as the latest advances, but also as current status or state of the issue. That is, there is a duality from the Spanish point of view to consider the state-of-the-art both the current situation and the most modern or the best. If we go to a more specific context, in our sector, we have two important references. The first is December 2015, which logically relates the state-of-the-art as the highest level of analytical performance technically obtained and indicate that this can be known through the selection of certain group, a certain percentage of laboratories. Our committee in 2016 defined the state-of-the-art as characterized performances by a certain group of laboratories in a given period. Consequently, there is a convergence between this proposal and our proposal, which is a selected group of laboratories versus a certain percentage of laboratories. In other words, we can take all the results, take a very large group, and talk about the state of the situation. Or we can take a very small group of the best laboratories, the most focused, the most accurate, and talk about the state of the art. Although it is true that in this proposal, our committee's proposal also defines a period. Finally, we have two questions to ask. The first, what percentage of laboratories should be chosen? We understand that depending on the percentage of laboratories chosen, we will have different performances, different specification values. And, on the other hand, also the time in which the study should be conducted to be considered. It would not be the same to work with a cycle as to work with 5 or more cycles to establish the state of the art. There are 3 known models we have been working with regarding the calculation of quality specifications for the state of the art. The first is the one that talks about, that takes into account a sample, results obtained from a sample or several samples. From there, the accuracy of these results is known and information is extracted. This is called the sample factor. On the other hand, there is another possibility in which a group of laboratories is selected, each given the same importance regardless of the number of results or samples they process, and conclusions are drawn from the results they provide. We call this the laboratory factor. Then there is a model that mixes both, where the organizer chooses one or another procedure depending on what is deemed appropriate for a given measurand. This will be explained by Dr. Ángel Salas in the next presentation, where a series of algorithms specifying this will be presented. To make the explanation easier, I present this chart. Each little circle represents a result, and all these little circles represent a cycle. So we can say that for a sample, which is in the vertical zone, there is a result. And for each laboratory in the long term, there is also a series of results. We can say that this laboratory has provided a group of results. For example, 8, another has provided 12, another has provided 3. That each of them will give information to obtain the quality specification. If we take only a single sample and look at the accuracy of each of the results, we can reach a conclusion, obtain a specification value. We can also take several samples and draw our conclusions, or we can use all the samples and consider each of the points equally weighted. This point or these results from this laboratory would be as important as this from another laboratory. This would be the first model, which is the result factor. We can also approach it so that laboratories can provide different numbers of results, but regardless of the number of results it delivers, they are equally weighted. That is, a laboratory with 8 results would be equally important in the calculation as one with 12 or 3. Finally, the third procedure is when both are mixed, 1 and 2, and then the specifications committee chooses which value to select, which is the value for the measurand. Logically, we can also consider results not chosen from a single cycle, but chosen from several cycles, and here we should also find differentiated results. We present several examples of results. For example, glucose, which is a common measurand. We know the sample for a single sample, the consensus value obtained, the standard deviation, the coefficient of variation, and we can follow procedure 1, which consists of defining for all these results which values are representative of the state of the art. And we can say, well, let's choose a representative of the state of the art, the result that represents 1% of the most focused. And here we have that we had a value, for example, if we only get 1% of the results, a value of 0.04% in percentage, or we could choose 10, that is, we consider representative 10% and choose. Then the specification value would be 0.04%. So we reach the first conclusion that depending on what we consider representative in terms of percentage of results, we would have different values. But also, what happens if we work with another sample, like the one we have here from 5 in 2015, with differentiated values, differentiated coefficients of variation? We find that the values would also be different. Why? Because we are probably in situations of different imprecision, different interlaboratory coefficient of variation in one sample to another by the concentration level we have. So, in addition to being different depending on what is considered representative in terms of percentage of results, there would also be differentiated values depending on the sample we bring. If we use the second model, which takes into account results but gives equal weight to the laboratories, regardless of the number of results each delivers, we find that depending on the percentage of laboratories considered representative, we would also have very differentiated specification values. In this case, the results are presented for glucose for 5 years, which represent 60 results. And we observe again that depending on the percentages of laboratories considered representative, we would have differentiated specification values. If we put it together, we see that depending on the procedure, we have differentiated specification values, even with the same sample or with differentiated samples. And this leads us to the conclusion that talking about the state of the art doesn't make sense as such. We must add an adjective after the word state of the art. State of the art obtained with so many results, with so many cycles, for this measurand and using a given methodology. If we also compare the value of the state of the art, for example, for different magnitudes, versus what we call the minimum consensus specifications, which is the maximum total error that 90% of the laboratories can achieve when processing 75% of the samples. In those with the least error, if we define this as the state of the art and compare it with the biological variation specifications, the desirable biological variation specifications, we define that, depending on the type of measurements, the minimum consensus quality specifications are stricter than those derived from biological variation for a certain group. This sounds normal because we are in situations, for example, in the case of biochemistry urines. So, logically, when we try to apply these specifications, choosing the quality specifications, we would choose the state of the art in this type of magnitudes. As conclusions, I would like to propose the following. 1. The Milan Agreement also establishes the use of the state of the art as a valid model with the perspective of being flexible. Different quality specification values obtained from the state of the art will depend on the model used and will depend on the group of laboratories used as a reference. And talking about the state-of-the-art quality specifications without saying how they were obtained doesn't make much sense. Third, if we compare the desirable quality specification values according to biological variation, they are not always stricter than the minimum consensus specifications. Logically, the desirable one has been used because it is not the one most used in laboratories. Finally, the bibliographies are articles produced over the years by the committee on which this presentation is based. I hope you like it. Excellent, Dr. Jorge Morancho Zaragoza. Very clear, very nice presentation. I will now give the floor to the second speaker, Dr. Ángel Manuel Salas García. Dr. Ángel Manuel Salas García is a technical engineer from the Polytechnic University of Catalonia, Terrassa, Barcelona. He holds a degree in chemical sciences from the Central University of Barcelona. He also holds a degree in biological sciences from the Central University of Barcelona. He is a specialist in clinical biochemistry from the Ministry of Education and Science. He has been a professor from 1974 to 2008 at the Higher Technical School of Industrial Engineers of Terrassa at the Polytechnic University of Catalonia. He worked at the Terrassa Hospital Consortium, Director of Quality and Patient Safety. He was Coordinator of Quality System between 2003 and 2014, and he is Secretary of the Foundation for Quality Control of Clinical Laboratories. He is also a member of the Interdisciplinary Committee of Quality Specifications. Dr. Ángel Manuel Salas García, welcome, and let's see your presentation. First of all, I want to thank Dr. Raúl Girardi at the International Federation of Clinical Chemistry for this invitation that allows us to present the activities we have been developing within the committee. Today, I will talk about the algorithm for obtaining minimum quality specifications, consensual. The structure I will give to my talk consists of, first, objectives, then what information we have, talk a little about total error, and then talk about a calculation process we call A. Then we will compare with a series of values from other countries, then the B process. I will present some results, conclusions, and bibliography. Already getting into the subject, objectives. The first thing we ask ourselves is what we want to achieve. So, what we want to achieve are minimum analytical quality specifications for Spain. And these, in principle, the characteristics we ask for or propose to achieve are that they are minimum analytical requirements that are mandatory in principle for laboratories. That is, and this, during the talk, I will insist a lot that if these minimum requirements are not met, patient safety is jeopardized. On the other hand, we will also want them to be aligned with some mandatory requirements from some countries, that it is plausible proposal, that it is in accordance with the reality of our country, and that it is based on scientific evidence. Following, also with the characteristics we want, there are specifications of the total error. And as the previous speaker commented, they are based on the state of the art. That is, we do not intend to replace Level 1 and Level 2 of the Milan Consensus Conference, but this is within what is Level 3 of the state of the art, and they are minimum declarations that each laboratory must comply with. The next step is what information we have. Then, look, over these years, we have been able to have the collaboration of a series of scientific societies, which I go on to comment. One is the Spanish Association of Medical Biopathology and Laboratory Medicine. Another is the Spanish Association of Clinical Laboratory. The third society is the Spanish Association of Laboratory Medicine. And the fourth is the Spanish Association of Hematology and Hemotherapy. To give you an idea of what this has meant, The number of laboratories involved over these years is over 4,000. So, in principle, we consider that we have representation from all over Spain. The first problem we faced was, do we have harmonized data from the societies? Of course, if we start mixing peppers with tomatoes, what we will get is sofrito, which is for cooking. However, we have been lucky. The different societies, the framework of action with the programs is very similar. And as an example, to show all these common points, I take as an example the serum biochemistry program. And we will comment on common aspects. First, they are all intercomparison programs. There is no assigned value. The values are defined by consensus. Within the different concentration levels, we have a wide range of values that even include critical values, which somehow help the doctor to make decisions. They are organizations that, in principle, do not propose a benefit and have interdependence from commercial interest. And also, the ethical criterion that societies have is a confidential use of the data. Let's continue with common aspects. They have anonymous participation. As I mentioned, the confidential aspect is rigorous. There is a monthly periodicity. I'm always talking about the serum biochemistry program. There are 12 samples. The data management is computerized. The duration is the calendar year, and certificates are issued to participants both for registration and active participation. And if we look at the computerized management aspect, we see that the computer system process is very similar to what exists in other organizations from other countries, where they usually work with the global mean or the peer group mean, which is always recommended to use this second point when possible. And now we enter into an aspect, the total error. We are going to work to determine the minimum consensus quality specifications for the total error. Then, for each measurement, we have to obtain the data provided by the different societies to make this calculation. And this calculation will be done with the total error expressed as a percentage, which will be the statistic we will work with. To give you an idea of the amount of data we have in a study conducted from 2005 to 2010, note that the number of data provided by the different societies approaches 5 million. This study allowed us to determine a series of specifications for 80 measurements. And within these measurements, we had basic biochemistry, special biochemistry, basic hematology, special hematology, and urine biochemistry. Here I only mention some important points. In 2020, for example, these specifications were updated and some more were added. So at that time, we have minimum consensus specifications for 143 measurements. In 2023, hematology and hemostasis specifications were updated, and we continue working on the subject. Let's look at the total error. The total error is a formula that is in all the books in the field we work in and is defined as the result of a laboratory minus the target result, divided by the target result and multiplied by 100 because it is expressed as a percentage. And in addition, absolute values, positive values are taken. What is the target value? It can be a mathematical mean, a consensus mean of the results from the laboratories. And in principle, I already told you that it is preferable to look for the peer group mean. But we can find ourselves in some situations where we have few data, and the committee decided that if the number of participating laboratories or the number of data we have is less than 10, the comparison is made on the global mean. I am always talking about specific measurement throughout the conference. And now we start to see what we do with these calculated total error values. Well, the first thing is what I have mentioned. The total error is calculated from the target value and expressed in absolute value. The second point is to make a graphical representation of these values. Once we have this graphical representation, the committee decides to eliminate the top 5% of the highest values. Why? Because it is considered that these high values can be due to transcription errors, unit errors, etc. And then, to avoid distorting the study, 5% is eliminated. And also, by committee agreement, with what remains, we look for the value that appears at the 95th percentile and call it the candidate minimum consensus specification. If this value has decimals, we round it to whole value. To give you an idea of what I have just said, this would be the distribution of the total error. Here we have the 5%. Here it has already been eliminated. We look for the 95th percentile and know that it is 10.02, so we round it to 10. Once we have this 95 percentile value, we refer to the mandatory compliance specifications, regulatory specifications from two countries, Germany, which are included in the Richtlinien, and the United States, which are also documented in the Clinical Laboratory Improvement Amendments. And then we do the following. We have a candidate value. We look for the data from Germany and the United States, and from all of them, we take the smallest quantitative value. If it turns out that the specification we initially chose is equal to the higher than the smallest value, this candidate specification becomes definitive, and this would be process A. We can also find that we conduct studies, we update specifications, and if we compare with previous periods of the same measurement, there may not be a significant difference between what comes out today and what came out time ago. Then we simply continue working with this value. But discrepancies may arise. In case of discrepancies, the latest study specification is taken. What I have just mentioned, well, I will represent a bit through the flow diagram. We have the start, then we have procedure A, and we see if there are mandatory specifications in Germany and the United States. As I mentioned, we have the candidate specification, and here we choose the lowest one we find in the bibliography. Then we ask ourselves, is it possible to make the comparison? It may be that there is no mandatory specification. Then the candidate specification goes directly to process B. Or is it possible to make the comparison and move to the next slide? If there is a significant difference or it is not possible to compare, we follow this path. Then we say, is the candidate specification equal to or higher than the mandatory compliance specification from Germany or the United States? If so, if it is, the candidate specification becomes definitive through 7. If not, the committee asks, are there reasons to accept this candidate specification? If the committee considers it acceptable, we follow this path, and the candidate becomes definitive. If there are no reasons, then we go to procedure B. Returning to the previous slide, we follow this path. Procedure B. Are there reasons to accept this candidate specification? If there aren't, the specification is discarded, and we finish here. If there are reasons, well, then let me explain about what procedure B involves. So, what does it consist of? I have told you that when the subject or candidate specification is lower than the smallest value that appears in Germany or the United States, we have to proceed with procedure B. What does this procedure involve? We have specification. This candidate specification will be incremented by 0.01% and renamed. We will now call it the error value test. With this value, we then check how many laboratories have 75% of their results meeting this error value specification. If the number of laboratories is less than 90, what do? We increment the error value test by another 0.1%. We keep doing this. It's explained here so you can see a bit. It is incremented by 0.01% and then called the error value test. We count the laboratories that have this specification meeting 75% of their results and move to the next point. It's the point here at the bottom. And we count the laboratories. If we have less than 90% of the laboratories, we go back and we make a new increment. Then we reach 90% of laboratories with 75% of their results meeting this error value test. This becomes the candidate and the final specification. Well, I would now like to present some results to you. You have seen that in the flow diagrams, there are a series of numbers. What we have done in the publication cited here is to show the path that each of these measurements has followed. Additionally, it will show if the final specification has followed procedure A or procedure B. Let me give you a couple of examples. Look, let's go to creatinine. We have 15 in CLIA and 20 in Germany. The lowest is 15. By procedure A, it is 20. Remember that procedure A is accepted if what comes out is equal to or greater than the lowest of the two. In this case, it is 15 and 20 is higher. The path that creatinine has followed in the flow diagram indicates that it ends up being process A. In this case, I should also mention that there was a previous value of 28, but since it is very discrepant, we stick with the value of the last study, which is 20. Let's move to glucose. Notice the smallest value is 10, but by process A we got 9, which is lower. This means we have to switch to procedure B. The procedure B gives us 11. There was a previous value of 10, but we consider that we should take 11. This is the entire path that glucose has followed in the diagram, in the glucose diagrams, and here we indicate that it was obtained through model B11. What conclusions can we draw from all this that I have explained to you? First, it is a model with a scientific basis, and due to the large number of results we have, we can start to think that it is a big data issue. With our experience, we have been able to apply this model to new programs, and we already have some experience in applying it to programs in other countries. I insist again on the most important point. These are minimum specifications that must be met. If they are not met, immediate corrective actions must be taken. Here I present the bibliography of some of our publications. I would like to point out that the first and second publications are in English, the rest are in Spanish. All are available, and we have more if anyone is interested in expanding this type of information. And simply, thank you very much for your attention. Excellent, Dr. Ángel Salas. It was very clear. Thank you very much. I will now introduce the next speaker, Dr. Enrique Prada de Medio. Dr. Enrique Prada de Medio is the Director of Cross-Cutting Procedures at the Integrated Care Management of Cuenca in Spain. He is the head of the Clinical Laboratory Service of the Integrated Care Management of Cuenca. He is a specialist in clinical analysis. He holds a degree in pharmacy from the University of Madrid. He is a member of the Interdisciplinary Expert Committee on Quality Specifications. He is a member of the Translation Group of the Technical Committee of ESOL Technical Committee for Clinical Laboratory and In Vitro Diagnostic Systems. He is the second Vice President of the Spanish Association of Medical Biopathology and Laboratory Medicine. And he is a member of the Do Not Do Working Group of the Spanish Ministry of Health. Dr. Enrique Prada de Medio, it is a pleasure to have you, and we listen to your presentation. Thank you very much, Raúl, for the introduction, and of course, thanks to the IFCC for the opportunity given to the committee to participate in these webinars. It is indeed a pride for me to participate in this type of event, and I hope not to disappoint the audience. I will talk about the state-of-the-art graphs and how we extract the minimum consensus specifications that my previous colleagues have been discussing, thanks to the state-of-the-art graphs. First, we will talk about how these graphs are constructed. Once we know how they are constructed, we will see the description of the same, what each axis and part of it means. We will see their usefulness. We will now see how, once we understood the graph's construction, how to obtain the minimum consensus specifications. Finally, I will show you the publication and, more specifically, the list of specifications we have published, which, as my colleague and friend Angel mentioned, is a free publication you can access without any problem. Let's start by talking about how the state-of-the-art graphs are constructed. The state-of-the-art based specifications simply reflect how a group of laboratories behaves at a given moment. For us, that moment is when that laboratory processes the control sample we have sent through the intercomparison programs, as we will see later. However, it is true that this same event, which is a specific event, the fact of measuring a control sample, if we analyze it over time, there will come a time when we can agree that the behavior of that laboratory is more or less uniform. Therefore, from there and from the set of laboratories, we can establish a proposed specification value, as Professor Ángel Salas said in the presentation. How do we construct these state-of-the-art graphs? Through the external quality evaluation programs, as mentioned earlier, we can know the total error, which is known through a simple formula that results from subtracting the result sent by the laboratory minus the target value, dividing it by the target value, and multiplying it by 100 to handle it in percentage terms. Therefore, it is possible to count the percentage of accumulated results each laboratory has within error margins as it analyzes samples sent over months and years. This way, we can fill our datum or dataset to build the state-of-the-art graphs. It is true that many strategies in calculating specifications mistakenly assume that laboratory behavior is always similar. All of us who work in laboratories know that not always when we process a control sample, that control sample falls within the quality specifications we have established. Therefore, we can assume that all laboratories behave similarly. I give an example related to what my colleagues have mentioned. If we have a data set and cut at the 90th percentile, it simply means that 90% of those results issued by all laboratories will be below that 90th percentile, as defined by the 90th percentile. But it does not mean that 90% of laboratories meet this condition. As I said before, some laboratories might have results within specification on some occasions, and the next day that control might not fall within the established specifications. This is very important to understand conceptually. To make all these concepts we have discussed in this webinar visible, we construct what we know as state-of-the-art graphs. The state-of-the-art graphs have been built thanks to the results of intercomparison programs from the 4th scientific societies in Spain related to clinical laboratories. As my colleagues mentioned, we have a volume of over 4,000 participating laboratories contributing nearly 5 million results, which we believe gives these state-of-the-art graphs significant robustness. How is the procedure carried out? First, obviously, we obtain the result each laboratory sends us after analyzing the control samples from external quality evaluation programs. With these results, we calculate the error assigned to each laboratory based on the target value achieved, which is the consensus value of all laboratories using the same methodology. Once we have all these errors, we can calculate the percentage of the total error committed by each participant in 100% of the control samples they process, 75% or 50%, considering that most of the time, as my colleague Jorge mentioned earlier, we usually have 12 cycles per year, because these cycles are monthly. From there, we can construct graphs from 50% to 100%. Once we more or less understand with which data these state-of-the-art graphs are constructed, let's visualize them. On one side, we have the y-axis, which will show us the percentage of laboratories capable of meeting the following condition, which is 50%, 75%, or 100% of their quality control results, below the total error marked on the x-axis. Obviously, the following circumstance occurs. As we increase the requirement for the percentage of results we want to count, the percentage of laboratories on the y-axis will decrease, meaning the curve will descend. Conversely, if we lower the percentage of results considered, the percentage of laboratories meeting this condition will increase. In this graph, it will surely be clearer. We can see how the exponential curve represented that 100% of laboratories have a certain error is much lower, so a smaller percentage of laboratories meet it than the curve above, which means 50%. In this curve, only half of the results would be below certain quality control value. Therefore, here it represents, as we said, the percentage of laboratories meeting a certain condition, and here on the x-axis it represents the total error that each laboratory would meet. What is the utility of these state-of-the-art graphs? Well, they can be given two approaches. On the one hand, we can see what percentage of laboratories can have a part of their results below an error, as we will now see. On the other hand, we can see what maximum error a certain percentage of laboratories can have when processing a certain number of quality control samples. Let's see it with some examples. First, we will simplify the curves to 75% and 100%, which are the most used by our committee. We set an error of 9% and we see what percentage of laboratories meet it. What we would have to do is draw a vertical line that would intersect both the 100% results line, marked with the green circle, and the 75% results curve. Then we would draw a horizontal line to extract these two conclusions. On the one hand, 45% of laboratories have 100% of their results below, in this case 9% for the determined measure, for example cholesterol, which would follow this curve. On the other hand, we can say that 90% of laboratories would have 75% of their quality control results below 9%. But we can read it the other way around. Let's see on this same curve what error the 95% of laboratories have. Well, 95% of laboratories in 75% of the control samples they process have an error of 13%. And what percentage of laboratories have that error below 13% in 100% of their samples? Well, in this case, it would be 63%. And as I said before, 95% of laboratories have 75% of the control samples they process below 13%. Therefore, with the state-of-the-art graph, we can know the maximum error percentage that a certain percentage of laboratories can achieve. An additional utility these graphs have is that they allow us to know in advance the difficulty level a certain specification obtained by a different model, as my colleagues mentioned, either by biological variation, a specification that comes from the legislative field, or from expert opinion. Since I know the state-of-the-art graph and they are known for each measure, I can see in advance, without error and following what was mentioned before, what percentage of laboratories will meet this condition. In this case, as we said before, 13%. Then 63% will have 100% of their control samples below that value obtained, let's imagine, legislatively, and 95% will have it in 75% of their samples. How do we obtain the minimum consensus specifications through these state-of-the-art graphs? Well, my colleagues have already been outlining our premise, our golden rule. As mentioned, the minimum consensus specifications belong to Model 3 of the Milan model, and what we have to do is, by using the state-of-the-art graphs, the total error given on the x-axis will be considered as the minimum consensus specification, provided it meets the condition mentioned, which is our mantra, that 90% of laboratories, which we will see starting from the y-axis, have 75% of their results, in our case, control samples, meeting this condition in 75% of their results, using the curve, the 75% below the value given by the x-axis. How will we do it? We'll go to the y-axis, the vertical axis, and draw a blue line, as you will see now, starting at 90%, leading to the 75% curve. When we reach that intersection point, we draw a vertical red line, and the value we obtain will be the minimum consensus specification that we will assume by the committee. Let's see some examples. Albumin in serum. We draw our blue line from the 90% y-axis, reach the 75% curve, draw our vertical line, and reach the x-axis. The specification we would obtain would be 11%, which is indeed the published value. Let's do the same exercise with calcium. We draw our line from 90%, reach the 75%, and go down the x-axis. In this case, we obtain not 9, but 9.1% in the graphical representation. And to conclude with the examples, we have triglycerides. We do the same exercise at 90%, reach the 75%, and this way go down to the x-axis and find that the specification would be 14%. Therefore, as we have the state-of-the-art graphs for all measures, because we have the data thanks to the intercomparison programs, we can have a complete list of minimum consensus specifications. This is published in the Laboratory Medicine Journal, a Spanish language journal published by the Spanish Association of Medical Biopathology and Laboratory Medicine, and the Spanish Clinical Laboratory Association. Here we have published 143 measurements, where you can see I have highlighted in yellow and blue the examples we have seen. These same examples could be repeated 143 times, which are the 143 measures we have associated. Well, some ideas to take home. I would say that we consider state-of-the-art graphs made with intercomparison programs, which, due to the large number of data we work with, we believe are quite robust. As you know, and as we have mentioned on several occasions, minimum consensus specifications are worked with the 75% curve of the results of those laboratories that meet a certain condition in 75% of their results. We are very proud because we believe the list of minimum consensus specifications achieved in Spain is very high, if not the highest, and we consider it is very useful for laboratories, not only in our country, but all over the world. Thank you very much. Excellent, Dr. Enrique Prada. We appreciate it. Let's see if all the members are here. Thank you to the three speakers. It has been very instructive, very agile, and important for laboratory application. You have a very agile method, easy to apply in the laboratory. I have something to say to Dr. Salas and Dr. Enrique Prada, who say that this could be applied to other countries. And, well, the model can be transferred to other countries. In my country, we are trying to apply it with different objectives, but it is perfectly applicable, which is important because although the data comes from Spain and the idea originates in Spain and the method comes from that country, it is perfectly applicable in other systems, provided there is the possibility of collecting large amount of data from external quality evaluations. Again, thank you. I think it has been very clear. I have some questions, and we will choose 3 to clarify and talk about some doubts. I have a question. What should a laboratory do if it does not meet the minimum consensus specifications? I don't know who can answer this. Well, I think I can talk about this topic. Let's see, we work in a healthcare setting, in healthcare entities, so we must never lose sight of the fact that our reference is the patient, and associated with the patient is their safety. So consider that these are minimum quality specifications that, if not met, pose a significant risk to the patient. What should be done? First, stop the process and do not deliver results. Then, according to what is established in the laboratory, if there is a quality management system, it is already specified what to do, either raising a non-conformity, a correction, or a corrective action. But what must be done, whether or not there is a quality system, is to see what happened and why it happened. Analyze it to find a solution so that this specific measure meets the specifications. Perfect, Dr. Salas. I have another question. Can state-of-the-art graphs be made with the results of internally managed but externally managed quality controls? Well, that is for me. It's a topic that in the various forums where we have talked about state-of-the-art graphs, I would say almost 100% of the time it comes up. Because it is true that the increase of this type of control in recent years, at least in Spain, has been very significant. Something I consider good. I think that moving from the classic controls manufactured by the reagent manufacturer to independent controls managed internally, or rather, internal control managed externally, I think it's good. The mistake several laboratories make is considering that this internally managed external control also serves as external control. They reduce cost, thinking they no longer need to be enrolled in any intercomparison program of any scientific society, because they believe that, well, since some external will do the calculations, or they are comparing themselves in some way with other laboratories, they are already meeting that quality requirement of external comparison in this way. And it is a major error, excuse my assertive expression, committed by many laboratories. The main reason is that when we participate in an external quality control, first, we all level up because we all send a single result. Therefore, by working with a single result, we all work with a total error, which is the data used to make the state-of-the-art graphs. So the answer is no, a resounding no. But I also take the opportunity to say that we cannot replace an external quality control, an inter-comparison program, with these internally managed external controls, because the way each laboratory may have when calculating the consensus mean of these programs may vary. There are laboratories that put internal controls once a day, others 3 times a day, others delete results and do not send them, others send all results. Therefore, we are not all playing with the same cards. So, consider it very important to clarify that these types of programs, under no circumstances, can replace inter-comparison programs, neither for making the state-of-the-art or establishing specifications, nor for anything. May I add a small comment, Enrique? Well, yes, because it's you. Also, in intercomparison, external controls, we don't know what the results will be. However, in the other model, by the second day, we already know what the results will be. True, indeed. Exactly, yes, with known values. The question is, would you see a result that you know diverges significantly from the expected results? There's the issue. Excellent. I have one more question. Let's see. Are the values obtained from a quality specification derived from biological variation always harder to meet than those derived from the state-of-the-art, the state of the technique? Let's see. It's a complex question, because in biological variation we have a range of possibilities. There is the optimal, the minimum, and the desirable, so you're not working with a single value. In the state-of-the-art, as I tried to explain, depending on how you define the group of laboratories or the results from which you will extract the data, as you define them, you will find different values. So, if we limit it to a model that would be, for example, quality specifications based on the state-of-the-art according to the laboratory factor, including the minimum consensus specification, and compared it, for example, to the desirable biological variation, we would find, as I tried to explain, that for some measures, this does not hold true. Biological variation is not always stricter. The key here is, as I mentioned in the 2014 Milan consensus, the idea is to choose the strictest specification from the set. I don't think if I answered, more detailed information would be needed to compare whether it is stricter or less strict. Perfect. Yes, I think so. May I add a comment, Raúl? Yes, go ahead. That question also, indeed, Jorge and Angel, comes up many times. One must take into account, let's say, the root, which is that the source of obtaining each of these specifications is completely different. They come from completely different fields. Therefore, the results you can get may be stricter or less strict. It will depend because of the methodology and specifically the source from which we obtain them is different. We are strong defenders of the state-of-the-art, not just because, but for what it means and applying it appropriately. Because it is true that sometimes the state-of-the-art, being in level 3, seems like, well, if you can't, you settle for the state-of-the-art, which is for everyone. And you find the surprise, as Jorge mentioned, that the state-of-the-art specifications seem very flexible and don't have to be. They can be as useful as biological variation or expert opinions. Remember that Angel stated that minimum consensus specifications must be met without exception. So, a scenario where a minimum consensus specification is stricter than a biological variation specification, which you find in urine biochemistry, makes you think that you cannot settle for meeting just one type of specification. But you would agree with me that if you say that in a laboratory forum that you follow state-of-the-art specification and another one says they follow biological variation specifications, it seems that the biological variation one has more importance than the state-of-the-art. And then, as you said, it has many nuances. And of course, this does not mean that biological variation specifications are not very focused on the patient's utility and their disease, which is the final objective of the laboratory. So, we are also strong defenders of them. Yes, keep in mind that these specifications are a starting point. In quality systems, we talk about continuous improvement. This means that one should not be satisfied because they meet this, but go further. It is about seeking a more demanding level, always achievable in the laboratory. Be careful with that. Well, thank you very much. Surely some more questions will arise. In any case, they will be answered by email. Thank you for attending this webinar, and thank you Dr. Salas Garcia, Dr. Morancho Zaragoza, and Dr. Prada de Medio for your interesting presentations that offer valuable information on the topic discussed. And of course, thanks to Dr. Fares Taye for coordinating this webinar and to the IFCC for offering this work for learning. Please remember that if there are questions and answers, they will be answered by email to those who ask them. The participation certificate will be offered at the end of this webinar after some questions. At the end of the questions, please click on Show My Score at the bottom of the page to get your certificate. Finally, on the on-demand content of this webinar, you will see that it will be available soon, and you will be informed by email. There will be other free IFCC webinars announced through the IFCC communication channels such as email, website, and social media. Thank you very much, and goodbye.